Namaskaram. Good afternoon all. Welcome to the teleconference program conducted by the Department of Chemistry, Faculty of Science, Dr. B.R. Ambedkar, Open University. This program is focusing on the title or topic liquid state. This topic belongs to UG second year semester 3 Chemistry 3 course. For this course containing this topic, to explain, we have two resource persons are there in our studio. Those are Dr. J. Mohan Babu, Assistant Professor, University College of Usmania University, Saifabad, and Dr. M. Keshavulu, Department of Chemistry, Assistant Professor, Avanthi Degree and PG College, Hyderabad. This program is of 60 minutes. In the first 40 minutes, we are going to explain the topic. Later, next 10-20 minutes, we will receive the questions from the audience to answer and also for interaction. For interaction, you need to call the following number 04023680456. Again, I am repeating 04023680456. Before going to the topic, our topic is liquid state. Before going to this topic, first we need to familiarize about the some fundamental aspects of matter. We know that what is matter? Matter is having some mass, it is occupies the some space, that is called matter. This matter can be divided into fundamentally three types. One is solid, liquid and gases. In addition to these three states, another two states are there. One is plasma and other one is Bose-Einstein matter. Okay, in recent studies we are considered these two states are also considered as states of matter. Now presently expressed as 5 states of matter, but fundamentally we studied about only 3 types of matters. The matter is of any state, that is very important in our day-to-day life as well as for the universe. If you consider solids in our life, we are taking food material and some other things, and also we are using some articles and instruments and home furniture, all is in the form of solid state. If you consider liquid, the liquids are very familiar. One is water. We know that how much important is of water. It is for ecosystem, it is for the survival of almost all living beings, and it is also for production purpose in the industry. And consider gas states or gases. These gases, we know that so many gases are dispersed in the atmosphere. These gases, for example, you take oxygen. This oxygen is helpful for the respiration of the human being, and also carbon dioxide. This carbon dioxide utilized by the plant kingdom. Therefore, for development of plant kingdom, it is useful. Similarly, we can use several kinds of gases in the production of several chemicals we are using day-to-day life. Those are used as in several ways. Example, drugs and medicines. Okay, these are the 3 different states. And other additional states are, one is the plasma. Plasma we generally see in the neon or sodium lamps. Okay, and also in the surface of sun. it is also found in several stars also. And when coming to the Bose-Einstein condensates, Bose-Einstein condensates, these are recently discovered and used in quantum computing for increasing and enhancing the speed of the processing of computers. Therefore, this matter is maybe any of state that is used in our day-to-day life and for the survival of the ecosystem and are also universe. Therefore, it is having a versatile usage. Due to that reason, we need to understand the properties of several kinds of matter to produce the new materials and to produce the several kinds of technologies, to produce the and uses of several kinds of articles around us. Therefore, I am asking Dr. J. Mohan Babu sir, please explain what is liquid state. Explain the various intramolecular forces present in the molecules of various states.
Yeah. So here the matter, so the generally matter, it is exists in the three states like solid, liquid and gaseous state. And the interesting fact of this, the matter is where we are listed solid, liquid and gases. So they will be interconvertible from one state to another state. And this interconversion is depending on the two factors here. One is thermal factor and another is the intermolecular forces. So depending on these two factors, the matter can be interconvertible here. And here, for example, if you take the solid compound, right? So if you apply a particular temperature here, then it will be converted into liquid. And beyond that temperature, on the higher temperature, so this liquid further converts into gaseous state here. That is a vapor state here, right? And this will be reversible. Like when you cool this particular gas or the vapor, so again it converts into liquid, and further cooling means upon the 0 or the -0 degrees temperature, so it is converting into solid state here. So in this way, these three types of matter is going to convert into one state to another state here. Now we will see how the intermolecular forces are affecting this interconversion and how they will be helpful to convert into one state to another state. So first we will see that in the liquid state, okay, so in the liquid state, when the molecules are interaction in between the same kind of molecule, then it is called the cohesion here. And when the molecules between, means the interaction of the molecules in the different molecules, like you take X and Y, okay, so then the interaction between the X particle and the Y particle, then it is called the adhesion here. Cohesion means the same molecule, the interaction between the same kind of molecules here. You take X and X or A and A, like that. And we can explain this phenomena by taking one example like the water droplets, okay, liquids, it is illustrating that particular cohesion effect, and the sticking of the two papers or the cloths, it is explaining the adhesion forces here. And generally these intermolecular forces, it will be decreases with increase of the distance in the molecule here, right? So if you see the distance of the molecules in the various states here, if you take the solid compound where the molecules are arranged very closely packed here, means no gap will be found in the solid state compounds. And in the liquids, you will see somewhat distances will be there, means the molecule will be loosely packed than whatever that particular solid here. And in the gaseous, very loose packing will be found in the gaseous state. That means the molecules will be arranged in a large gap here. Okay. So first we will see what are the intermolecular forces. So the generally here the intermolecular forces means various types are there. We can see the dipole-dipole interactions and hydrogen bonding interactions and ion dipolar interactions and van der Waal interactions here. So these are the intermolecular forces here. Generally we aware about the bonding connectivity of the atoms. For example, we have the three types of bonding connectivity here in between the atoms. Sorry, in the atoms we can find the three kind of interactions. Like if you see the ionic interaction, where the ionic interaction forms between the more electronegative atom and the less electronegative atom, or the more electropositive atom here. For example, if you take the NaCl here, okay, where the sodium and the chlorine, where the sodium is carrying the positive charge and the chlorine is carrying the negative charge. That means the chlorine is having the high electronegative nature and the sodium is a high electropositive nature here. So both the atoms combine together and it forms the ionic bonding here. And if you take the like ammonium, ammonium hydroxide here, or the ammonium molecule, so where the ammonium molecule is, it is going to form the coordination covalent bond here, where one atom is having the empty orbital and the another atom or the group is having the excess of electrons here. So it will be donates the electron to the atom which is carrying the empty orbital, and it is going to form a coordination covalent bond here. And the third type of bonding interaction is, you can see the covalent bonding, where the covalent bonding is forming due to the sharing of electrons here. That means where both the atoms which are capable to form a bond here. So both the atoms are having the each electrons here, equal number of electrons, and both the atoms donates a one electron and both will be forms a bond here. Means the mutual sharing of the electron, they will form the bonding by mutual sharing of the electron. So these are the three types of bonding bonds found in between the atoms here. But here the intermolecular forces are different from the bonding interactions here. The intermolecular forces are, these are weak interactions, where the listed like ionic interaction and covalent interactions, coordination covalent interaction, these are the where the strong interactions here, and the intermolecular forces are weak interactions, and it will be found between the molecule to molecular here. And due to these intermolecular forces, the molecules held together and it forms a definite geometry to the particular matter, like solid or the liquid or the gases here. Okay, so we will see one by one the intermolecular forces here. For example, here first we will see the ion dipolar interactions. So ion dipolar interactions. So what is ion dipolar interactions? So here the ion means how the ions are going to form when a means the stable compound is undergoing heterolytic cleavage. When the stable compound, like you take NaCl or the HCl here, when it is undergoing the heterolytic cleavage, then the one atom is taking the electrons and it is gaining a partial negative charge, and it is called as a cation here, and another atom is losing the electron and it is gaining the positive charge, and it is called as the cation here. So the excess of electron atom is called as a anion, and another one is a cation here. So when these cations and anions are interacts with the stable molecule like water or any other stable molecule, then it forms a ion dipolar interactions. Okay, dipolar, so the name itself is telling dipole means two different charges, pole means charges here, dipolar means two charges. If you take the water, for example here the water, I will explain with the model, like here this is the water molecule here, just you assume this is the water molecule, where this is the oxygen and these two are the hydrogen, because the water molecular formula is H2O, where this is the oxygen, and you know that the oxygen carrying the 2 lone pair electrons, and the hydrogens are attached to the oxygen here, okay, and the oxygen is a more electronegative in nature, and the hydrogens are like it is attached to the oxygen, okay. So this particular oxygen, right, because due to the more electronegativity nature, so it attracts the bond electrons towards itself, so it is gaining the partial negative charge delta minus here, charge will be forms on the oxygen, and the delta positive charge will be forms on the hydrogen here. Then this is the polar molecule, okay. So this is the polar molecule here, and earlier I told that where the NaCl, the 2 cation and anions are forming here. So when the cation or anion here, when they are come closer to the water molecule here, then they will form a interaction, ion dipolar interaction with the cation or the anion. For example, here just to assume it is a NaCl, this is the sodium, this is the chlorine for example, and this is the water molecule. When for example this is the chlorine which is carrying the negative charge here, partial negative charge delta minus, and this is the hydrogen, it is carrying the partial positive charge here, right. So this particular chlorine is interacts with the hydrogen, it forms a yes, interaction here, intermolecular interaction, right, and generally yes, and but this interaction is not possible because the chlorine is it is a partial negative charge, and the oxygen also partial negative charge. So the repulsion will be takes place here, no interaction will be takes place, right. So you can see the repulsion between the same kind of electronegative atoms here. So the interaction will be possible between the chlorine and the hydrogen here. So this kind of interaction, intermolecular interaction, is called the ion dipolar interaction. This is the ion and this is the dipole molecule here, okay. This is one kind of intermolecular forces here, and another is a dipole interactions. So dipole interactions, like you take this is the HCl molecule or the NaCl molecule, you take, means the polar molecule, it should be polar, okay. Polar means whose dipole moment does not 0, okay, does not equal to 0, right. So if the dipole magnetic momentum is 0, then it is a polar molecule, non-polar molecule, and magnetic momentum is not it is not 0, then it is polar molecule here, and it able to form the opposite charges like positive and the negative charges here. For example, here is a NaCl molecule here, and another NaCl molecule is going to interact with this NaCl molecule, then it will be forms a dipole interaction, because this is the neutral molecule with 2 poles, and another molecule also same kind of molecule, or it may be different here. So this is also having the dipoles here, then you can see the dipole interactions, right. And this is one kind of intermolecular forces here. And one more interaction is the London dispersion forces, and it is somewhat different than your ion dipole interaction and dipole interaction, where the London dispersion forces will be forms in between the 2 non-polar molecules. The previous 2 forces are the forms between the polar molecules here. Here the London dispersion forces observed in between the 2 non-polar molecules. So what are the non-polar molecules generally? Non-polar molecule means no electronegativity difference between the bonded atoms. For example, you take helium molecule, this is the helium molecule, right. So this is the helium molecule, this is also helium molecule, okay. Where the helium molecule is having the right same kind of yes, atoms here, right. So for example, you take hydrogen also, you can take the hydrogen molecule, this is hydrogen, this is hydrogen, okay. So hydrogen molecule hits hydrogen and hydrogen, because the molecule means 2 atoms, okay. The combination of the 2 atoms is the molecule here. So where the bonded atoms are the same, with the same properties, same electronegativity nature, and everything is same. So there is no difference in the electronegativity and any other properties here. So you cannot so it won't forms a positive negative charges here. That's why it is a non-polar molecule. Then how it will be converts into polar molecule. Okay, so we called that is the induced polar molecule here. So we are inducing the polarity in the molecule. So how it will be generated? Yes, polarizable due to the polarizability. So it forms a, it converts into the non-polar molecule converts into polar molecule here, because generally you know that the electrons in the orbital, it is continuously revolving around that axis here. So at a particular time, right? So at a particular time where the electron density becomes more on one side and the electron density becomes less on another side here. Okay, you can see, for example, this is the hydrogen molecule or the helium, you can take anything. So but it should be equal electronegativity nature here. Okay, it should be the homodiatomic molecule. It should be homodiatomic molecule. So we are taking the, I am taking the homodiatomic molecule here, where it is having the same kind of atoms here. So when the electrons are, okay, revolving around that, so at a particular time where the electron density becomes more at this point and the electron density becomes less at this point here, then what happens here? Where the electron density more means it is going to convert as, it is forming a partial negative charge here, because the excess of electron always it is denoted with the delta and minus, and this side where the electron density is less, so you can indicate with the delta plus here, then it is becoming the polar molecule, and this kind of polarity we call the induced dipole moment, induced dipolar molecule here, right? So in that case where the two induced dipole moment molecules approaches together, then the London dispersion forces will be observed. This is the third kind of interaction here, intermolecular interaction. And next one is a hydrogen bonding interaction, where the hydrogen bonding interaction will be observed in between the hydrogen and the hydrogen which is attached to the more electronegative atoms like nitrogen, oxygen, fluorine here. Okay, so just you observe, when the hydrogen, okay, the hydrogen when it is interacting with the hydrogen which is attached with the more electronegative atom, okay, the hydrogen must be attached with the more electronegative atom like oxygen or the nitrogen or fluorine. Okay, for example, HF, hydrogen fluoride, or the water molecules like water molecule here, right? So this in the water molecule you see this is the oxygen attached with the hydrogen. Okay, so this hydrogen it able to form the hydrogen bonding. Okay, for example, if you take this kind of, this is the hydrogen or the helium, whatever, the homodiatomic molecule, when this is the hydrogen, this is hydrogen, then it won't form hydrogen bonding because they both are same homodiatomic molecule. So it won't able to right, it won't able to form the bonding here, hydrogen bonding. Okay,
self polarization is absent.
Yes, self polarization. So this is the hydrogen bonding interest. So these four forces are explaining the means the states of the matter like solid, liquid and gases here. So the intermolecular forces and the thermal energy, okay, these two are the main factors to explain the states of matter. And now we'll moving to the differences of the solids, liquids and gases here. Okay, so here we will see the how these three types of states are differentiated here from each other here. You take solid, liquids and gases, and we are seeing some properties here. First we will see the shape. Okay, shape. So generally for this solid compound they have a fixed volume. Okay, so they have a fixed shape here. Okay, like you take wood or you take any solid material. Okay, you take wood or you can take any mobile or cube, whatever, right? So it is having a fixed shape here, and also it have a fixed volume. And the liquid, coming to the liquid, so liquid also having a fixed volume. Okay, for example, if you take 2 liters of liquid in one container, Okay, when you transfer the 2 liter in another container or the beaker, so same volume will be transferred to the another beaker. So it have a fixed volume. And the gases, generally the gases does not have the fixed volume here, okay, because the atom or the molecule arrangement in the gaseous phase is very loosely, okay. So when you transfer these particular molecules from one container to another container, the molecule will going to escape from that container. So the volume is going to decrease or the increase, so that thing will be happen. So you don't have a fixed volume and you don't have a fixed shape also. And in the liquids, the where the shape, okay, shape is, it is acquiring the shape of the container, right. So for example, if you pour the water or the liquid water, anything, water or the oil, when you pour the water in a triangle container, so you will, it will acquire a triangle shape here. And if you pour the water or the liquid in a rectangle container, so it acquires a rectangle shape here. So it is acquiring the shape of that particular container here. And the gases, they don't have a fixed shape and the volume. And the intermolecular forces of attraction, generally in the solid molecules, in the solid state, the intermolecular forces are maximum. Due to this reason, it is very rigid in the nature. The solids are very rigid. You cannot break the solids. For example, this is the table. You cannot break this table easily. You can break, but so much you can yes, you can apply the excess of energy to break that one. That means this is due to the intermolecular forces are very strongly held the atoms or the molecules here. And in the liquid, it is medium to the solids and the liquid. It is having the intermolecular forces, but not much than the solid one. It is having, it is a medium, yes. It is a medium medium kind of intermolecular forces. And in the gases, the intermolecular forces are very less, very minimum, because where the molecules arranged in a spatially, they are arranged in a spatially, disorderless here. Yes. That's why the no interaction will be takes place between the molecules. And the molecular movement of the molecules, generally for the solids, generally the you cannot see the movement here, because they are very rigid nature, so the molecule cannot move, but due to the internal energy, so the molecule will be right, so they will move to the mean to its mean point here. And in the liquids, you can see the Brownian movement. You can see the Brownian movement. So you can you are aware of the Brownian movements. It is a random kind of movement here. And in the gases, you can see the random movement is observed. And the fluidity. So generally the solids cannot flow, right? Solids cannot flow because they have the fixed position and fixed state here. And the liquids, they will flow, okay, they can be flow. Liquids will be flow, but the flowing will be higher level to the lower level. You can see the rivers or any right. So water, when you pour the water, so it will flow from lower means up to down. And the gases, they have generally they also can flow. Okay, they also can flow, but it flow in all direction. For example, if you you take the bromine, right? If you open the bromine means if you open the cap of the container or the beaker, right? So the bromine will be diffuse very speedily, okay, very rapidly. It will be diffuse in the entire of your room. That is where the diffusion rate is high for the gases. So it can be flow, but it is rapid. And yes, here you can see the diffusion, okay, like here the diffusion, generally the solid don't have the diffusion rate of diffusion here, and the liquids having the slight diffusion rate, okay, and the gases having the high diffusion rate here. Okay, sir, okay. So these are the differences of these solids, liquids and gases.
Okay. Okay, as per SAR discussion, the states are existing in matter is existing in 3 states. It is in solid, liquid and gases. It is more affected by the internal attraction or repulsive forces for the existence of these 3 kinds of fundamental states of matter. If the attraction force are more, they are existing in the form of solids, that is closely packed and orderly arranged of that particles in the matter. That is the reason they are arranged in the form of solid. And if the these attraction forces are less and repulsive forces are more, they are existing, the particles are existing in the matter in somewhat distant manner, but they are having some attraction forces, they are attached to each other, but they are not broken, they are existing in the form of liquid. When you coming to the gases, the particles in between, the particle distance is more, the attraction forces as well as repulsive forces both are negligible. They are most of the time exist as a free particles. They are, due to this reason, in the solids the particles will not move easily. In the case of liquid state, the particles can able to move but completely not detached from the other attached particle. These are all imaginary interaction or repulsive forces only. Okay. In the case of gases, it will not exist, therefore it is freely move in all the directions. When you coming to the shapes, every solid matter is having particular shape, whether it is in the crystal or amorphous in nature, but it is having some shape and some volume. But in the case of liquids, there is no shape, because the particles will not persist in a fixed position. Due to that reason, when you take in any vessel, that vessel shape is that matter, liquid shape, liquid's shape. But it is having volume, because we are taking some volume of container, that volume is occupied by this matter, liquid matter. Due to that reason, it is having volume, but there is no shape. But in the case of gases, there is no shape, but we need to preserve it in the closed vessels, in the packed and closed vessel. Then only we can observe it is existing with some gas in that cylinder, like that. Okay, these are based on that we can classify the matter, whether it is a solid or liquid or gases. Okay, then I am asking Keshavulu sir, please explain various properties of liquids.
So liquids possess various properties like vapor pressure, surface tension, viscosity, optical activity and refractive index. So what is the vapor pressure means? Whenever the liquids are equilibrium with vapors, that means the condition it should be attained between rate of vaporization is equals to rate of condensation. Rate of vaporization of liquid means as we provide the temperature, liquid becomes converted into the vapors. At the same time, as we decrease the temperature, vapors also again condensed into the liquids. At a particular state, the rate of condensation is equals to rate of evaporation. So such condition is known as equilibrium. So at equilibrium position, the molecules of gases are exerts pressure, which is known as vapor pressure. So then coming to the part of surface area. So before going to know the surface area, we have to know the interface between the matter. So means whether the matter can be exist in solid state, liquid state and gaseous state. So whenever the interaction between the liquids or interaction between liquid with the solid or gas, what type of interactions will be present? So then the interaction of liquid to liquid. So if there is a partial miscible liquids or immiscible liquids. Immiscible liquids means they won't dissolve with each other. So means if we may add two type of liquids in one container, they form individual layers. The space which will be present between the two layers is known as interface. So how that interface will be related to the surface means that particular liquid has the interface with another substances like solids or gases. For example, the liquid may has interface with the gaseous molecules, so that may be denoted with the surface. So at the surface, how many number of molecules are present and what are the molecules are present at interface and what type of interactions are present between those molecules. As sir said, intermolecular interactions are present. So there are many type of intermolecular interactions. The intermolecular interaction between the molecules may be due to hydrogen bonding, or may be due to dipolar nature of the liquid, or that may be due to ion dipole nature, or sometimes it may be London dispersion forces. So then coming to the part of viscosity. So means the surface tension, how we can define the surface tension means whenever the surface molecule is observed in the liquid. So for example, if you take some amount of liquid in a container, so in a bulk solution molecules are present, and at the surface level also molecules are present. So in case of bulk solution, so there are equal interactions with the other molecules. There are completely equal interaction with the other molecules. Due to that equal interactions, the center molecule may be holded with other all surrounded molecules. That's why the water droplets are present in a spherical shape. So that means whenever we consider the bulk phenomenon, so inside the liquid solution, so the equal interactions will be present between the molecules. Due to that equal interactions, the surrounding molecules holded by the one central molecule, so that defines the spherical shape of the droplets, water droplets. And when we coming to the part of the surface area, at that particular surface only bottom side direction attractions will be present, no attractions on the above of the liquid. So because the vapor phase is present, so there is no attractions in that vapor phase. So means some of the attractions we are missing in that area of surface. So the remaining area that will be below to the liquid means some of the molecules are attracting of the surface molecule, which leads to the decreasing the surface area of the surface molecule. So the tension which is arised, so due to decreasing the surface area in that particular unit, which is known as surface area. So and also it can be defined with F force by area. So how many number of intermolecular interactions are present of that surface molecule, and in that particular area how many number of molecules will be present. If we find out that ratio, so that can give the surface tension. So then coming to the part of the viscosity. Viscosity means, as sir said, so the intermolecular interactions will be present between the liquid molecules. So if those liquid molecules are very close to each other, or that may be far with some distance. So there are very close to each other means, that are tightly bonded means, so that viscosity becomes more. So as we compare the variation, if we consider the water liquid and consider oil and consider grease molecule or honey. So there are three different substances will be there. So honey will be more viscous in nature. So then compared to oil will be more viscous nature compared with water. So how we will observe this thing? So means simply take the three substances like water, oil and honey simply thrown on the floor. So which will move fast? So water will be move fast. Then compared to oil will be little bit move fast then compared to honey. So that means the more viscous that can be replaced with, so the internal resistance of the flow of the liquid. So the viscosity, it should be measured as the internal resistance to the flow of the liquid. So that kind of property is known as viscosity. Then so whenever a liquid will be there, if we may pass a polarized light on the liquid, so that may be rotates either right side or left side. So means there is a rotation of polarization of the light which reflects the optical activity. So and also the refractive index. So the refractive index measures the how much light it will be bent, means whenever the light is passing through the liquid solution, how much it will be bent, so that can indicate refractive index. So as we discussed that, so the surface tension may be in the bulk phenomena and surface molecules, how the molecules are behaving at a surface level and how molecules are behaving at a internal part of the liquid. So that may be different due to due to cohesion properties. Means cohesion means like molecule interactions. Like molecule interactions means if we consider water molecules, same type of water molecules will be present in the liquid. So therefore the interaction between the two water molecules becomes cohesion. So due to that cohesion, one water molecule that may be surrounded with interaction with many number of water molecules. So due to that interaction of surrounding of water molecules, so the water droplet may be held in a spherical shape. So and interfacial tension means if two different solutions or else immiscible liquids, one liquid is mixed with another liquid, so there is no mix up of those two liquids which forms two different phases. So the interaction between these two phases may called interface. So even at the time of interface, how many number of molecules will be present on that particular area, then what will be the force is applied on that area, so that will be considered as interface tension. So only the liquid molecule is interacting with the gases, means the surface interacting with the gases, that will give surface tension. So the one liquid is interacting with the other liquid, so that particular region may express the interfacial tension. So there are many methods are helpful to determine the surface area of the surface tension of the liquid. So that surface tension of the liquid may be depends on surface area of the liquid and also temperature and also intermolecular interactions. If the surface area of the liquid will be increases, its surface tension will be decreases, that are universally proportional with each other, and also as the temperature of the liquid is increases, that becomes converted into the gases. So therefore as increasing the temperature also, the surface tension will be decreases, because many number of liquid molecules are converted into gases. So then one more main important factor, that is the intermolecular forces. As the intermolecular forces are directly proportional to the surface tension. If intermolecular forces are strong, so there is a high surface tension of the molecules. So this can be explained with the help of one method, that is the capillary rise method. Capillary rise method can be used to measure the surface tension of the liquid. Right. So in this, so simply take some liquid in a beaker and dip the capillary into that. So what will observe means simply the liquid which will be moved in the capillary. So sum of the height. So how much of height will be moved in the capillary liquid, so that may be due to the interactions in between the water. For example, the liquid is water interactions are observed in the liquid. So but in case of capillary, inside the capillary, so the glass and water interactions will be present. So these gas and water interactions are known as what? Adhesion interactions, adhesion property. Water interactions are cohesion property. So as compared to the cohesion property, adhesion property will be strong. So due to that strong interaction between the inner surface of the glass and water, so the water which will be flow up. How much of height it will be take with respect to that? So we have to measure the surface tension of the liquids, right. So as the water will be moving up, means the force which will be supported to the weight of the water. So means how much of water will be moving in the capillary with respect to that. So the circumference, and there may be water forms a concave. So concave, then if we may consider instead of water mercury, that will be convex. So means that concave and convex, with the help of concave and convex merciness with respect to that, so we can get the circumstances of the liquid droplet is equals to its weight, which is helpful to flow the water from bottom of the capillary to height of the capillary. That can be denoted with, so 2 pi r gamma is equals to pi r square into h g into rho. So h is the height, g is the specific gravity, r is the radius, and so the 2 pi r is the circumstances. With respect to that, we can get the relation, so that is gamma is equals to half hg rho r. With the help of this equation, we have to measure the surface tension with the help of capillary rise method. So and one more method is there. So whenever the capillary should be considered with a bubble, right, with a bubble, and it will be passed through from one to another solution. So where the water droplets or liquid droplets will be there, that liquid droplets are spherical in shape due to cohesive interactions between the molecules. So according to the Hankins-Brown, so they may observe that so liquids, how many water droplets are coming to the bottom, so that weight of the water droplet is equals to so force applied on the opposite side. So means if we may consider the equilibrium condition, so whenever from the capillary from top to bottom liquid it will be coming, so what was the weight of the water droplet, that is equals to force which is acting opposite side on the capillary tube. So that force may be mg, and the weight of that 2 pi gamma into r, radius of the water droplet. So this equation may be applied for the two liquid solutions. So with the help of that, by doing ratio, we can get the relation between surface tension and mass of the water droplets. So that is m1 by m2 is equals to gamma 1 by gamma 2. So with the help of this, the ratio of surface tensions of two liquids can be measured. So this is the method of drop weight method. So then coming to the part of one more main important property of that, as we discussed, viscosity. Viscosity we already discussed that is the internal resistance of the flow of the liquid is defined as viscosity. So the units of viscosity are the pi's, and that viscosity may be depends on the whenever the three substances like water, honey, oil which are simply thrown on the floor, so it will be moved. So how much distance it will be covered, and what is the force which will be acting on that. The resistance, due to resistance it can stop the flow of the liquids, that indicates with property of the viscosity. So means the area is multiplied with its velocity gradient. Velocity gradient means what will be the change in velocity of the liquid, so that is with respect to the how much distance it will be covered. So that is the ratio gives velocity gradient, then the force which is directly proportional to the area and velocity gradient. So from that, the proportionality constant can be replaced with some constant, that is the eta. That eta indicates viscosity of the liquid solution. So that eta is equals to f by a into dx by dv. So as we apply all the units on that, so we can get so various units. So dynes per centimeter into second, or grams per centimeter square and second, and also 1 poise equals to gram per centimeter per second. So these are the units of the viscosity. So there is a one method to determine the viscosity with the help of Ostwald viscometer. So what was the setup of the Ostwald viscometer? With the help of that Ostwald viscometer, how we have to measure the viscosity nature of the liquids. So the Ostwald viscometer, so there is a one bubbled means, so there are in the instruments capillary tube, U type of capillary tube with two bulbs will be there. So one bulb denoted with A and B, and another bulb denoted with C. There are so one upper mark and lower mark at first bulb A and B, then the C bulb will be empty. Initially the liquid solution that will be filled in that, how much time it will take to flow from A point to point C, point A to point T, how much time it will take, and also it will depends on the density. So the viscosity, rate of flow of matter from one place to another place, that can be expressed with one equation, that is eta is equals to pi p r power 4 into T by 8 V L. So where So r is the radius, time is the time taken to flow of water from one place to another place. So that means from point A to point C. And for this equation is applied for the two liquids, one of the liquid viscosity will be known with respect to that reference one, the another liquid solution viscosity can be measured. So that with the help of equation eta 1 by eta 2 is equals to T1 d1 by T2 d2. So where T1 and T2 are the time taken for flow of liquid from A to C, and these are the densities which are applied for such liquids. With the help of this, one of the liquid should be considered as viscosity. For example, sulfuric acid is the liquid, or else any other liquid solutions we may consider. Water is the reference one. So when water is passing in the capillary tube, it will take how much time? So that should be considered as the reference one. So then our viscosity liquid, liquid we have to know the viscosity. Such liquids are passing in that capillary tube, how much time it will take to move from A to C. With respect to that time, we have to measure the viscosity of the liquid solutions. So these are the main two properties are applicable for the liquid solutions, which may explains with the help of its intermolecular interactions.
Okay, sir. Okay, the liquids are also showing the different properties based on the internal forces, attractive or repulsion forces. Commonly it is showing surface tension, internal tension, optical activity, refractive index, like viscosity properties. Okay, sir, now I am asking Mohan Babu sir, please explain what are liquid crystals, how they can be classified.
So here the liquid crystals. So generally already we are aware about the states of matter, like solid, liquid and gaseous. So here the liquid crystals are, it is a mesomorphic state of the matter. It is an intermediate between the solids and liquids here. It is an intermediate state between the solids and liquids here. That means it is exhibiting the liquid properties as well as the solid properties. Like you can say it is a colloidal kind of morphology is observed. And you can see here in the structure, it is showing a very interesting characteristic here. So by taking the liquid crystal, upon cooling, so you will get the crystalline solid here, and upon heating, so it is converting into liquid. That means it is a intermediate between the solids and liquids here. And generally here the liquid crystals, it is having variety of applications in the regular life here, and we will see the different phases of these liquid crystals and how these liquid crystals are classified. So first we will see the liquid crystals. Generally it is classified into three types here, and that basically it is two types. Basically the classification is two types, like thermographic liquid crystals and leiomorphic liquid crystals here. And the thermographic liquid crystals further classified into three types here. One is pneumatic liquid crystals, semiotic liquid crystals and holistic liquid crystals. And how these three types of liquid crystals are classified and what is the differences between these three types of liquid crystals here. Here the classification of these three types of liquid crystals based on the two factors. One is the oriental order and the positional order. So based on these two factors, we are classifying liquid crystals into three phases, like pneumatic phase, semiotic phase and cholesteric phase here. First we will see the pneumatic phase. Here the pneumatic phase, you can see the picture of that pneumatic phase. So where it appears, it look like say the marble texture, marble texture. So you can see the in the house, right? So in the houses you can see the marbles where you can see that the zigzag nature of the design you will be observed. So here also the pneumatic texture, pneumatic phases, it is having that kind of texture, and here the molecules arrangement is in different ways. Okay, so where it is exhibiting the positional order and it is not having the oriental order, right? For example, here you see these are the three molecules here. Okay, these are the three molecules, just to assume, right? So where here the three molecules are, right? So the three molecules are aligned on the same axis. Okay, these are aligned in the same axis here. Okay, so same direction, these are aligned in the same direction. So you can say the positional order here, right? And the oriental order, for example, here these two molecules are in this direction and another molecule is in this direction here. So you can see the disorder, you can observe the disorder here. So it is, there is no in the order. Okay, so you can see this kind of phenomena in the pneumatic phase liquid crystals. And semiotic phase liquid crystals, you can see it is exhibiting both properties like positional order and oriental order, because the molecules arrangement in the same direction and they will be having the same position also. They have the directionally, they are properly oriented, and the position also in a proper position you can observe in the somatic phase liquid crystals. And in the cholesteric phase liquid crystals, you can see that means it is exhibiting both properties, like some phases having the pneumatic phase properties and some phases exhibiting the somatic phase properties here. So it is intermediate to both things here. So these are the different types of liquid crystals and their phases here.
Okay, sir. Yeah, well explained the definition of liquid crystals. There is the intermediate state of liquid and a solid crystal. Okay, it may be equilibrium in between at a certain temperature also, but it is having a very various and valuable applications. Now I am asking Keshav sir, can you explain the applications of liquid crystals?
Right. So nowadays we are using liquid crystals as LCDs. So just we are observing in television. So there are previously LCDs, then later on that will be converted into LEDs. So liquid crystal display. LCD means liquid crystal display. So in many televisions we use it as a liquid crystals for making the displays of the instruments, and also which can be used to identify the tumors, cancer tumors or cancer disease, right? So liquid crystals are helpful to identification of the cancer tumors and cancer cells and so many other tumors. What type of tumors will be present in the body? So all kind of tumors will be observed with the help of liquid crystals. So then the liquid crystals are pneumatic, sematic and cholesteric. So this may be differentiated with the orientation. So with the help of the variation of orientation and position, so there are huge applications in electronics and so some other medicinal applications also will be present.
Okay. Now in the entire 1 hour session we are discussed about the various matter states and especially we are concentrating on the liquid state. We are discussed about the how the liquid state is exist and what are the main factors of the liquid states to exist in its state, and what are the